On behalf of Space Education and Research Foundation, and on my personal behalf, I'm very happy to welcome again Professor Som Kumar Sharma and all the participants from different countries who are participating in this series of talks on LIDAR science and technology. And today is the second talk. Yesterday, you all heard Professor Som Kumar Sharma speak on the first introductory talk, and there he elaborated on the atmospheric structure and the kind of studies that need to be made or are being made world over, and also the techniques that are being employed to study the atmosphere. And today's talk will be the world of atmospheric LIDAR, and this has two parts. Today is the first part, and tomorrow this will continue as second part. And before I hand over the mic to Professor Som Kumar Sharma to speak to you on this topic, which is very important and good, and he's an expert of that, let me say a few words about him, though I introduced him yesterday to all of you, but I would say that he is doing a very great deal of work on LIDAR and the application of LIDAR for atmospheric studies. He is establishing a chain of stations in India and has collaboration even outside. And with this LIDAR network, we expect that there will be a lot of good new research, new results that will come and that we will get to know about the atmosphere and very soon. And Professor Som Kumar Sharma had a very excellent academic career, both up to his master's degree in physics at Lucknow University, and also during his PhD, which he worked at Physical Research Laboratory and got degree from Gujarat University. He has done very excellent work, and since then he has been doing good work, and at present an associate professor at Physical Research Laboratory. And he has been, for his excellent work, has been adequately awarded by IAGA, COSPAR, and ORSI, and he has been continuously organizing atmospheric science sessions at AOGS for several years. And with these few words, let me now request Professor Som Kumar Sharma to start his talk. Professor Som Kumar Sharma, please.
Thank you, Professor Vas, for a very nice introduction. Once again, today I welcome all my webinar colleagues who are connected to us for the today's talk, which is on the world of atmospheric LIDAR part 1. It is under the aegis of Space Education and Research Foundation. So I am thankful to SERF and the director of SERF, Professor Hariom Vas, who gave me this opportunity to discuss with you about a very pertinent topic, which is a need of hour for around, you can say, globe. Now the era is there to study the atmosphere or anything in great detail, with more precision, with more resolution. So in that part, the LIDAR is one of the best, or you can say state-of-art tool for the investigations of various physical, chemical, and radiative processes which are taking place in the atmosphere. That before I start today's talk, I would like to give a very brief recap what I discussed in yesterday. This will be very helpful for our webinar colleagues who joined today, or you can say it will interconnect the yesterday's talk with the today's talk. So it is sort of a recap on the previous talk that was yesterday on 9 September 2019. So yesterday I discussed various aspects of the Earth atmosphere. In detail, I discussed about the atmospheric composition, and in composition I emphasize upon what are the major and minor gases and what are their importance. And most importantly, I discussed with how the ocean fluxes, or you can say the gases which are coming out from the ocean, and you can say our surface also breathe. So with the breathing of our land surface, how it interacts with the atmosphere. So this we discussed yesterday. Then the most important, like density, pressure and temperature variation in the earth atmosphere. Then greenhouse gases and their impact on the atmospheric processes. Vertical and horizontal mixings in the atmosphere, because as I described, there is no physical boundary exists in the atmosphere, neither in the vertical direction nor in the latitudinal or longitudinal direction, or you can say the lateral. There is no boundary into the atmosphere. So that's what the vertical and horizontal mixing of different species processes becomes very important. Then, as you know, that weather and climate, the most fascinating and important topic in the earth atmosphere, that I discussed the earth atmospheric weather and climate. What are the differences between weather and climate, and what are the parameters are required to in-depth study of the weather phenomena, and if you sum the weather phenomena, then it becomes the climatic processes. Then, you know, sun is a source of energy and source of life, because life without energy, you know that what it meaning. So if you are energetic, then life is energetic and more active. The sun gives lot of energy to us, and that also in different wavelengths, or you can say in the different compartments, and these compartments are very useful for us. So I discussed the electromagnetic spectrum, radiations, and their role in the earth atmospheric radiation budget I described briefly. And then finally, yesterday I talked about what are the major techniques. Please remember, these are the major tools and techniques for the investigation of the vertical structure of the earth atmosphere up to higher heights, you can say up to mesopause or even 100 kilometer, 110 kilometer. And majorly it was like the in situ techniques and the remote sensing techniques. Then I just gave the glimpse of the major instrument technique for investigation of the atmosphere, such as balloons, ground-based balloons, rockets, radars, lidars, satellite, and many more. There are many more, spectrometer, photometer, and so many instruments are there for active and passive remote sensing of the Earth. Again, I will say here one important thing. The remote sensing is a very, very important technique and effective technique for studying the atmosphere, because the places where you cannot go, or you can say they are inaccessible by any in situ measurement, then you can send your signal, or you can send your delegate like a signal, and it will bring back the information. So remote sensing is one of the very important and strong tool for atmospheric investigations, and it is being very effectively utilized for the science, academic purpose, and most importantly for the benefit of the humankind. The remote sensing techniques are being utilized. So with this recap, I will start my today's presentation, and in this I will start again with the concept of remote sensing. I gave yesterday a detailed description, but again I will say the remote sensing is the science and technology of obtaining information about an object without having the sensor in direct physical contact with the object. This is a simple definition of the remote sensing, and this is exactly opposite to the in situ methods. Opposite to the in situ method. Here I will introduce one more term, that is basically the effective, or you can say true remote sensing. And what is effective remote sensing? That means sometime when you send the signal, so you want the natural information of that place. I can give example. Suppose in some region you want to measure the temperature. You want to measure temperature at 30 kilometer altitude. So your signal should bring back the natural temperature what is at that time at 30 kilometer. The signal should not disturb the originality of that medium and bring the information which is disturbed information. So in the remote sensors, one has to be very careful in designing these remote sensors, or you can say remote sensing tools and technique. The remote sensing tools and technique should not disturb the naturality of the medium while taking the information or while you're bringing back the information. It should not be deformed. That is effective and effective remote sensing without altering the naturality of the medium, or you can say the object. So radiations interacting with an object to acquire its information are remotely, and that, as I told yesterday, radar and lidar. Then sonar is also there, sonar is also there. Basically, sonar is sound detection and ranging, radar is a radio wave, or you can say radio, it's not wave, radio wave detection and ranging, and lidar is light detection and ranging. And you know the sonar is there, sound navigation and ranging. So these all where there is a lidar, sonar, and sonar, these all are very effective active remote sensing tool. If you see, these are active remote sensing tools and technique. In the passive remote sensing, the telescopes which are used for astronomical purpose for collecting the light, are photometers, spectrometers which are being used to collect the air glow or aurora processes. These are the passive remote sensors. But here the lidar is fully utilized, or you can say one of these tool for active remote sensing. So for further moving ahead, word of lidar. Lidar stands for light detection and ranging. Once again, I will say that many times we get confused like that. Lidar is a laser detection and ranging. No, lidar is a light detection and ranging, and the laser is a very good unique source of light. So today, in further of my talk, I will give little description of why laser, why not other light. I will give just glimpses of that today within our discussion. Before I start anything about the lidar, I would like to say one thing. When any light wave, when any light signal, I will say rather, any light signal, when it passes through the any medium or vacuum, whatever it is, when it passes through the medium, then there are several processes are taking place, and these processes are attenuation, scattering, reflection, absorption, etc. So these are the four major processes: attenuation, scattering, reflection, and absorption. So these are the basically optical interaction with the atmospheric constituent or atmospheric, you can say, entities. So attenuation, scattering, reflection, and absorption. Either one will take place or all will take place simultaneously. One will be more, one will be less. Sometimes scattering is more, absorption is less. Sometimes attenuation is more, scattering is less. Sometimes signal is fully reflected, sometimes it is absorbed, like that. So when any light passes through any medium, then these processes take place. And these processes are very effectively being utilized to study that medium. So as I term the like that, scattering. Scattering is like the, you can say, scattering of the light. So scattering of light is, again, there is a two types of scattering. One scattering is you see the elastic scattering, and another one is the inelastic scattering. So here I would like to say few things about elastic and inelastic scattering and how we are will be using in the lidar. So elastic scattering, very simple tool is like that. When the transmitted wavelength and back scattered wavelength which you are receiving are having the same value, or you can say there is no shift in the wavelength in the transmitted and received signal, that scattering is known as elastic scattering. Example is like, suppose if one signal is being pumped at 532 nanometer, one laser light is being pumped at 532 nanometer, and the backscattered light which is being received again it at 532 nanometer, then it is known as elastic scattering. So here if you see diagrammatically, if you see the left hand side panel, then absorption, fluorescence, and all the things are here. Okay, there is a change in the energy level. atomic absorption, resonance, fluorescence, these things are there. I will discuss later. But here, if you see on the right hand side, then there is a very good example of the Rayleigh scattering, elastic scattering and inelastic scattering. So the Rayleigh scattering discovered by Lord Rayleigh, which is taking place from the neutral atoms and molecules, that is Rayleigh scattering. It is elastic. If you see that that the excitation levels and that again the de-excitation level, both are coming from the same, you can say, levels. So the wavelength, or you can say energy, here and here, both are same. So E is equal to HCF1 lambda. So the wavelength which is transmitted, same wavelength, or you can say the similar wavelength, is scattered back. That is Rayleigh scattering. Another scattering is a Mie scattering. Mie scattering takes place from the bigger particulate matters like aerosols and dust, etc. That is also, I will describe in detail. That is also a elastic scattering. There is no change in wavelength in Rayleigh scattering and in Mie scattering. But if you move further and go to this one, Raman scattering, here you can say the excitation level is like that, goes to upper level, and when it comes back, it is not coming to the ground level, it is here. So there is a basically increase or decrease of energy. So that way the Raman scattering is inelastic scattering. An example I can see, if you pump or transmit wavelength lambda, then the most of the signal will come in the elastic scattering at wavelength lambda, but some wavelength will be coming lambda plus delta lambda and lambda minus delta lambda. Stokes line and anti-Stokes line, that is the Raman scattered line, and it is a property of the material. So the in Raman scattering, there is a shift in the wavelength. So that scattering is known as an elastic scattering. So please remember, in the elastic scattering, there is no change in the wavelength, means the transmitted and scattered, or you can say received signal, is the same wavelength. And in the Raman scattering, that is inelastic scattering, the transmitted wavelength and the received wavelength there is a difference. There is a shift in the wavelength in the when you are receiving it. That is the Raman scattering. So simply remember, elastic scattering, when there is no shift in the wavelength in transmitted and received, that is elastic. When there is a shift in wavelength, then it is inelastic scattering. Under elastic scattering, as I told, there is a Rayleigh scattering and Mie scattering. Rayleigh scattering takes place from very tiny particulate matters, like very neutral atmosphere, which are very small. And the condition for Rayleigh scattering is very simple. When the size of the scatterer is much smaller than the wavelength, or you can say transmitted wavelength, or you can say wavelength which is illuminating that molecule or atom, then Rayleigh scattering takes place. The condition is, if the size of the scatterer is very small in comparison to the wavelength, then Rayleigh scattering will take place, and that happens in the neutral atmosphere. The species in the atmosphere like nitrogen, oxygen, these all are satisfying this criterion. So in the neutral atmosphere, mostly the Rayleigh scattering takes place, and that's what you know. The sky is blue due to Rayleigh scattering, and that scattering takes place from nitrogen, oxygen, and other gases present into the atmosphere. Then there is a Mie scattering, and Mie scattering is again elastic scattering, and Mie scattering takes place when the size of scatterer is little bigger than the neutral atmosphere. So if the size of the scatterer is comparable to the wavelength, then basically Mie scattering takes place. And as I told, the Raman scattering is an entire different word discovered by Professor Raman, great C.V. Raman, which he was basically awarded the Nobel Prize for the discovery of Raman effect. So it was on Raman effect that is out of the scope of today's discussion. So just remember, it was discovered by Professor C.V. Raman, and it is a very useful technique for studying the atmosphere different constituents. You can study the different constituent by using the Raman scattering, and that LIDAR is known as Raman LIDAR. I will come later. And then of course absorption and fluorescence takes place from the virtual level. I will discuss these things probably little later. To move further ahead, as I told that first was scattering. How scattering is like elastic and inelastic. Then just I introduce the Mie scattering and different type of scattering. So in that, the important thing is that what is a backscatter cross section and what is the mechanism by which the signal you are getting. Because in LIDAR or in any receiving technique, the most important thing is how and how much signal you are getting back. How and how much signal you are getting back. So that depend upon various factors, and one most important factor is the backscatter cross section of that species, like whether it is nitrogen or oxygen or aerosol or dust particle or soot or cloud droplets, whatever it is. So that is the backscatter cross section. So here if you see the Mie scattering which takes from aerosol, the scattering cross section here is order of, you can say, 10 to power minus 8 to 10 to power minus 19 centimeter square per steradian. Okay, so that you can say it is relatively big. The in Mie scattering, the scattering cross section of aerosol particles like that is relatively big, and mechanism here for Mie scattering is two photon process, and it is elastic scattering and it is instantaneous. Please remember, in the Mie scattering, in first panel, if you see first row, if you see Mie scattering which takes place from bigger particles like aerosol, soots and all these things, the scattering cross section is 10 to power minus 8 to 10 to power minus 19 centimeter square per steradian, and this scattering happens due to two photon processes. That is out of the scope of today's talk. What is the two photon process? Maybe some other time I will describe this thing. What is the two photon process? What is single photon process, and so on. But today I will focus on mostly on the how these scattering processes are exploited in the LIDAR. So the two photon process, elastic scattering, and it is instantaneous. Please remember. Then if you come on the second row, then it is atomic absorption and resonance and fluorescence. And there basically again, if you see the scattering, cross section is 10 to the power minus 13 centimeter square plus steradian. It is two single photon process, absorption and it is spontaneous emission, and it is delayed and depend upon the radiative lifetime. Basically the fluorescence and basically resonance, this thing absorption one is delayed. It is not instantaneous, and scattering cross section is order of 10 to the power minus 13. And then next one is coming the molecular absorption, fluorescence from molecules, liquids and solids. Molecular absorption means fluorescence from molecules, liquids and solids. So molecular absorption is again, it is order of 10 to the power minus 19 centimeter square per steradian, and this is again single photon process. Fluorescence from molecule, liquid and solid, as I told, again 10 to the power minus 19, and it is two single photon process. Inelastic scattering, please remember, fluorescence is inelastic scattering and delay and depend upon the lifetime of that species. Fine. And then I am coming to the most important thing, which is very effectively, you can say, used for neutral atmospheric exploration from 30 kilometer, or you can say 25 kilometer up to 90 kilometer. That is Rayleigh scattering. And Rayleigh scattering cross section, please remember, it is order of 10 to the power minus 27 centimeter square per steradian. And again, this is a two photon process. It is elastic scattering and it is instantaneous. Now I will recall, if you go in the first row, Mie scattering, also it is a two photon process, elastic and instantaneous. And Rayleigh scattering is also a two photon process, elastic scattering and instantaneous. Both are elastic, both are instantaneous, and both are two photon process. Then what is the major difference? Major difference lies here. You see the Mie scattering cross section is a much bigger, about 10 order of magnitude bigger than the Rayleigh scattering cross section. So please remember, in Mie scattering we get a very strong signal. In Rayleigh scattering we get relatively weaker signal. So the scattering cross section here comes into the picture. Mie scattering cross section is very big here compared to the Rayleigh scattering cross section. Rayleigh scattering cross section is, remember, is about 10 order magnitude is less. If you take here 10 to the power minus 17 in middle, here it is 10 to the power minus 27 centimeter square per steradian. And then Last but not least, it is coming Raman scattering. This is basically wavelength dependent, as you know, and the scattering cross section is much smaller than even Rayleigh scattering cross section, and the order of the scattering cross section in Raman scattering is order of 10 power minus 30 or minus 32 centimeter square per steradian. This is again two photon process. It is inelastic scattering and instantaneous. So this basically Raman scattering, Rayleigh scattering, and Mie scattering. These three are very effectively used in LIDAR. And here again you remember, if the Raman scattering cross section is even 3 order of magnitude, or you can say 3 to 4 order of magnitude smaller than the Rayleigh scattering. So if you see Mie scattering 10 to power minus 19, Rayleigh scattering 10 to power minus 27, and Raman scattering 10 to power minus 30 or even lower 10 to power minus 32 or so. So the getting signal through Raman scattering is extremely difficult. Okay, and I will describe these things in detail in my coming slides. So please remember these things, that there is a similarity between Mie scattering and Rayleigh scattering because they are almost similar except there is scattering cross section. Both are two photon process, elastic scattering, and they are instantaneous. But if you go to the Raman scattering, there are two differences major. The scattering cross section is smaller in the Raman scattering cross section. In Raman scattering, this is also two photon process, and it is inelastic scattering. This is a major difference. Inelastic, and this is also a instantaneous process. Now I will move further and I will introduce you the most important component of the LIDAR. The most important. Every component is important, but you know, engine. Every component of the train is important, whether it is coaches or wheels or passengers. But engine, without engine, things becomes dull. Okay, so in the LIDAR, there are two major things: transmitter and receiver. In the transmitter, it is laser, and receiver is a telescope that I will come later. So before I move further, it will be nice if you listen little bit about the lasers. Laser is a unique source of light. Okay, and it is nowadays used in various facets of our science, technology, and in life. So laser, if you see the slide is in front of you, laser stands for light amplification by stimulated emission of radiation. Like LIDAR is light detection and ranging, and laser is light amplification by stimulated emissions of radiation. And laser is really, the word of laser is again very fascinating. And laser is a device that produces a coherent beam of optical radiations by stimulating electronic, ionic, or molecular transitions to higher energy levels. And when they return to the lower energy level by stimulating emission, they emit energy, and that is the basic concept behind the laser. So light amplification by stimulated emissions of radiation. So radiation is required, light is required, and it is being amplified, and stimulated emissions of radiation is coming out. So sorry. So please remember, the laser is a very major part of the LIDAR. And why laser? The question comes, why laser? Why not a simple searchlight can be effectively used in the LIDAR? Why laser? That you will come to know just within few minutes. So laser, it is a unique source of light. Laser is a unique source of light. And few things, if you see, the light emitted from laser is a monochromatic. I will explain in detail what is the monochromaticity and what is the other thing. So light emitted from laser is a monochromatic light, and monochromatic means monochrome. Mono means single, chrome means color. Single color. Single color means one wavelength. So it is a one color, or you can say single wavelength. Pure wavelength, single one color. Red is red, green is green. Only one wavelength. There is no mixing in that. So it is monochromatic. It is monochromatic means it is one color or wavelength. And in wherever it is written in green, it is basically comparison with the ordinary light. In contrast, ordinary white light is a combination of many colors. Many colors means many wavelengths of light. So the laser has one color and one wavelength. Ordinary light has many colors means many wavelengths. Then second property of the laser. Laser emits light that is highly directional. If it is highly directional, you can point it anywhere. So highly directional means that is the laser light is emitted as a relatively narrow beam and you can put in a specific direction. So the laser light is highly directional and that laser light is emitted as a relatively narrow beam and is in a specific direction. Contrary to it, ordinary light, it is a light bulb, emits in many directions and away from the source. Okay, so many directions away from the source. I will illustrate this more diagrammatically in few slides. And third, very important property of laser is the light from laser is highly coherent. And coherency is a very good, you can say, phenomena which make things very, you can say, effective. So the laser is highly coherent. Coherent means that the wavelength of the laser light are in phase in space and time. So if there is no change in the phase of different wave packets, then that is coherency. I will explain further diagrammatically. The coherency means wavelength of the laser light are in phase in space and time. Contrary to it, ordinary light is a mixture of many wavelengths. So there is no coherency. There is no coherency. And these 3 points I would like to emphasize. These above properties: monochromatic, directionality, and coherency. So highly monochromatic, highly directional, and highly coherent. These 3 properties make the laser light unique. As I told, the laser is a unique source of light. So what makes the laser light source unique? It is its monochromaticity, directionality, and coherency. So these 3 properties of laser light make it very versatile and useful and unique. And laser light can deposit a lot of energy within a small area without affecting the neighboring area, or you can say medium. So this is also a beautiful property of the laser light. The laser light can deposit a lot of energy within a small area. And last one, the lot of profits are coming to you by using laser light. But of course, when there are profits, there are some losses are there, or you can say one has to be very careful about using the laser. If you read the last line here, which is written in the left, laser is more hazardous than ordinary light. So you have to use this very good light source, unique source, very carefully, because it is more hazardous and sometimes life threatening. Okay, so one has to be careful. Though ordinary light is not, you can say, so coherent, so directional, so monochromatic, but it is not hazardous. So these are the properties of laser. You please keep in mind, due to this, the laser is a very versatile source of light and very effectively it is being used in our LIDAR tools and technique. So little bit more about the laser, more diagrammatically, it will give you the feeling how the incandescent bulb means ordinary bulb. If you see how it is known as incandescent bulb, because there is a filament and that filament is basically glowing and heated up, and due to that heat the light come out. That is incandescent bulb, and that you see the light vectors and light is going in all the direction, like here and all these things. So in contrast to this, if you compare with the laser light comes and goes very coherently in that one direction. Here you see the directionality is lost. So here if you see these incandescent things which are coming out from bulb, major 3 things: many wavelength, multi-directional, and it is incoherent. That is light coming from the bulb. If you go to the laser light, it is highly monochromatic, it is highly directional, and it is highly coherent. So this answers the question why laser is being used in lidars. So its monochromaticity, its highly directionality and coherency makes it a useful source of lidar. Moving further, little bit. What is monochromaticity? I told verbally, but if you see diagrammatically, it will get printed in your mind. What is monochromaticity? If you see here, if it is lambda, if you see it is blue light, it is blue light. If you take the blue light and plot it like that, you can see this is the wave. Okay, and here if you see the wavelength of, if you see in the spectrum, violet to red. In the red, the wavelength is basically increasing. So you can see here the wavelength is shorter and here wavelength is longer. So this is red light, this is blue light. Okay, so you can say the blue light and red light, they are separately having different wavelengths, you see, and different frequency. You see different frequency of the blue light and red light. And if it is monochromatic, the only blue will be there, only one wavelength. If it will be red, then it will be only red, only one wavelength, only one frequency. Okay, but in the white light, these type of several colors are mixed, or you can several wavelengths are mixed. So there are several frequencies are mixed. So the monochrome is not monochromatic light, it's a non-monochromatic. So in monochromaticity means blue is blue, red is red, like that, single color, single wavelength, single frequency. And another one, if you see the directionality, if you see this is laser light, you can pump in highly in one direction. Okay, highly directional beam. It is very narrow and very less divergent. Though I will not say it's non-divergent, because it is almost impossible to have non-divergent laser beam, but highly non-divergent. So here you can see in the beginning the beam width is this much, and if you see at large distances the beam width increases. So there is a very little divergence in the laser light. So this is monochromaticity, this is directionality. Contrast to it, if you see the bulb, this is the laser light going in this direction. In the bulb, the light is going in all the directions. Okay, so this is highly non-directional in the ordinary light, and laser light is highly directional. And monochromaticity means single color. And this is a conventional light source is there, this one. And beam divergence, as I told you, see this yellow dot is small and this big, means here beam diameter, if you see, is this much, and here beam diameter is this much, means there is a little bit of divergence in the laser beam when it propagated to the longer distances. And the simple formula for beam divergence theta d is equal to beta lambda upon d, where beta is almost 1 for type of light amplitude, distribution, definition, or beam diameter. For a given light, you can take beta is equal to 1. Then the beam divergence depend upon wavelength and beam diameter. So you can very simply calculate how much beam divergence will be there by knowing these small, you can say, properties of the light. I will move ahead further, and concept of coherency is shown here. If you see the incoherent light source here, you see if there, this is red, blue, green, violet, green, blue, and yellow also. So see there is a light waves are there, and these are, you see their faces are, this is face up, here this is face down, and so on. It look like that, very haphazard. There is no coherency, or you can say there is no systematic change in their phase, or you can say their peaks and troughs, or you can say the crust and troughs. So this is incoherent light wave. And if you see contrast to it, coherent light wave, all the faces are together. Here if it is face up, all faces are up. If it is face down, all faces are down. So you see that they are moving independently but coherently. You see that all the faces are coherent with each other. So this is ordinary, from ordinary light source, and this is from laser light source. So this is a, you can say, the pictorial view of coherent light wave and incoherent light wave. So please, I hope that now the monochromatic, few things I'll go back. If you see the monochromaticity, it is clear to you. Directionality is clear to you, and then last one is the coherency is clear to you. So these three things makes the laser very versatile, very useful, and very effective in various atmospheric research processes, and most importantly in the LIDAR tools and technique. And of course, the laser is again you can say like word of LIDAR. There is a word of laser. Of course, in future I will be coming to you with word of laser also. But here I will give the basic concept of laser, like that, how it happens, how it is highly monochromatic, how it is highly directional, how it is coherent. So here there is a few principles are shown here, like absorption, spontaneous emission, stimulated emission, and population inversion. So these are basically the, you can say, the concept, physics behind the laser is there. So what is absorption? Simple. You see, it is pictorially shown here. The light is absorbed, that electron goes up, it absorbs light, it goes up to the excited state. This is E1, this is E2. After absorbing light, it goes to higher state. Then spontaneous emission, once it has gone to the higher state, it will come down. When it will come down, then again it will emit the energy E is equal to SC upon lambda. And that depends upon delta E, the energy difference between E1 and E2. That is delta E is equal to SC upon lambda. So this will come. And then stimulated emission. That is important because in laser, stimulated emission and population inversion, they are heart of the laser. That basically basic science behind laser is stimulated emission and population inversion. Our laser happens due to stimulated emission and population inversion, not by spontaneous emission. So stimulated emission and population inversion. So you see, stimulated emission means you see absorption and spontaneous emission. Now you are stimulating emission. So instead of one photon, two photons are coming out. So it's like one photon was stimulated to emit, and that both are in phase and coherent. So this is stimulated. Last one is a population inversion. Population inversion means the inverted. Inverted means higher energy level, or you can say the number of photons in higher energy level is more than the number in the, sorry, here it is typo, number in the lower energy level. This is typo here, it should be, please read it lower. So number in higher energy level is more than number in lower energy level. Please this read you as a lower. So number in higher energy level is greater than number in the lower energy level. That is the population inversion. Of course, when I will discuss the word of laser, then I will describe these things in great detail. Then you will become the laser experts also, as you will become the LIDAR experts today and tomorrow. Moving further, this was about laser. Now laser has been used, and I am coming back to LIDAR. LIDAR is light detection and ranging again. So what happens? The powerful laser beam is pumped into the atmosphere, and once it is pumped, then light is absorbed, attenuated, scattered, all the processes are taking place. Then back scattered light is received by the telescope from different altitudes, and when the back scattered light is received, then you get the useful information about that altitude. Suppose laser beam is going and signal is coming from 15 kilometers, so it will bring back signal information from 15 kilometers. Suppose coming back from about 50 kilometers, it will bring back from 50 kilometers, and you can say full entire range you can cover. So this is just a diagram, and this is basically different type of scattering has been shown here, like basically different layers. So these are the, this peak is due to aerosol, this is due to Rayleigh, and this is basically meteor trail, and this is by sodium LIDAR or metallic LIDAR, which I will describe. This is due to resonance. This peak is coming due to resonance of the laser beam with the atomic metal atoms present at that altitude, about 90 kilometers or so. Fine. Here one thing is very important. What is the working principle of LIDAR? So LIDAR works on the principle similar to the radar. Radar means radio detection and ranging. LIDAR is a light detection and ranging. So the working principle of LIDAR is like radar. Radar measures the time delay between the transmitted and received pulse. So LIDAR measures the time delay between the transmitted and received light signal. That is the working principle of LIDAR. The LIDAR measures the time delay between the transmitted and received light, and you know that LIDAR is light detection and ranging. So it transmitted, detected, and now range. Range means altitude or horizontal range you want to detect. So how you can detect? Very simple formula. You might have read in the very earlier classes. Distance is equal to velocity into time. Distance is equal to velocity into time. This is a simple formula. Here if you say distance is equal to height or range, so range is equal to velocity into time. And you know the light travels with, you can say laser travels with velocity of light, and velocity of light is known. It is 3 into 10 to the power 8 meter per second. So that is known. So what is unknown? Unknown is only time. So if you come to know time by some device, then you can calculate the range. So range is equal to 3 into 10 to the power 8 meter per second, that is velocity, into time. You want time, and that time delay, or you can, the time is measured by the radar or LIDAR. Simply you can get the range. So the formula is written, the time of light r is equal to what? R range, R altitude, whatever you say. R is, C is the velocity of light, and then it is multiplied by delta t, how much time it took. But you see here it is divided by 2. It is very simple. Why it is divided by 2? Because if you see, signal is going and coming back, so it is taking double time. Going, time t1, coming back, again time t1, it becomes 2t1. So you have to divide. If you want to calculate the distance, one way distance, then you have to divide by 2. So the range is equal to C delta t by 2. Why? Because going and coming back. Signal goes and comes back. So please remember, LIDAR pumps highly monochromatic laser beam into the atmosphere. The backscattered signal is temporarily received, and the time is recorded. With that time in LIDAR, the range is calculated from what altitude the signal is coming. That is being estimated by using the LIDAR. Moving further, the LIDAR has different configurations. You can have the bistatic LIDAR, that is known as a bistatic LIDAR, means bistatic configuration. Bistatic means the transmitter is located at one place and the receiver is located at another place. So usually the transmitter is laser beam or searchlights, and the receivers are, you know, for optics or the telescopes. So the bistatic configuration is like this. The laser signal is transmitted here, and usually these are continuous wave lasers. Okay, continuous wave lasers are searchlights, and then you have telescope, and with the telescope you are probing this, you can say, volume. Here you see, if you are tilting the telescope in the one direction, then you are probing only this volume. But what you want? You want the vertical distribution. So then there is a mechanism by which you can tilt this telescope. So this telescope can be tilted this direction and in this direction. So by tilting the telescope, you can get the information here, 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 by changing the angle of the tilt of the telescope by using the continuous laser. Continuous laser or searchlight is pumped into atmosphere, and you are tilting the laser like this, changing the angle of the tilt. Then you are getting information here, 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 and like that, so on. But here you see, the problem is, here the probing volume is small. As you are going up, the beam is diverging, so the probing volume increases. So beyond certain altitude, it is difficult to probe the atmosphere by using this technique. In LIDAR, that is basically another LIDAR. It is a monostatic configuration. In monostatic configuration, the transmitter and receiver both are together. Okay, and again you see, R is equal to range is equal to C into delta t by 2. Means this range, very easily you calculate. C is the velocity of light, and delta t, time is measured by this, and divide by 2 means coming and going back. Signal goes and comes back. That's what it is covering, the 2R. So R is equal to this by 2. Okay, so here in the monostatic configuration, the laser, or you can say transmitter and telescope, both are together. Both are almost on same frame. So here is this laser beam is pulse, bump, and with the telescope from this altitude, or you can say from all the altitude, you are receiving the signal. Here A is a area of the telescope, delta Z is a vertical resolution, what volume you are illuminating, and Z is the altitude. So this is a monostatic configuration when you are having the transmitter and receiver together in the LIDAR, and in the biostatic configuration you have the transmitter and receiver separated, and mostly in the biostatic configurations continuous wave searchlights are being used, and in monostatic configuration nanosecond laser pulses are being transmitted, and you get the vertical distribution of various constituents and information about various process and person. So I hope it is clear. The LIDAR configuration, there are two configurations. One is a biostatic when the transmitter and receivers are separated, and another is a monostatic when the transmitter and receivers are together, and mostly the pulse laser are being used in the monostatic configuration, and in the biostatic configuration mostly the continuous wave laser sources are being used in the LiDAR system. Now moving ahead, I am coming to little more, you can say, detail how the LIDAR remote sensing, the interaction with the atmosphere. As I told, the scattering, absorption, reflection, attenuation, these things are taking place. So this is little bit busy plot, or you can say the slide is there. I will try to decode it like that. Here if you see this beta, lambda, lambda L, theta, don't go with the jugglery. The delta R is basically range. So this is basically interaction with the atmosphere. When I will come to that LIDAR equation, this change will be very clear to you. Please remember, I will come back again to this slide. The interaction between radiation and object. This is related with what? Beta, scattering cross section, and other properties of the material which is available into the atmosphere. Then you see the radiation propagation through the medium. Radiation propagation is like this is transmitter. Transmitter is transmitting, and when it is being transmitted, then there is a basically transmittance. It depends upon wavelength and range. Okay, and then another side you are receiving, again signal propagating through medium. So this is, you can say, LIDAR. LIDAR is transmitting, interaction taking place, back scatter signal is coming back, and it is received. So how the science is there? So here is the, basically this is the property of the material available, or composition of the atmosphere, nitrogen, oxygen, aerosols. That beta is different. Scattering cross sections are basically, or absorption, or reflection, or whatever process that is basically related to the atmosphere. And then this is T. T means transmittance, and that depends upon wavelength and range. Range means this distance. When the radiation transmitted, there are interactions. When the backscatter signal is coming, then again signal propagating through medium. So here also, when transmitting, the signal is propagating through medium, it interacts. When coming back, then also signal propagates through medium, it is received. So this is transmitter is a laser source, radiation source, receiver, light collection and detection. So here the in transmitter, basically there is a how many photons, how much power you are pumping into the atmosphere, and here how much you are collecting, and that collection will depend upon the area of the telescope, or you can the solid angle A upon R square. The solid angle is subtended by the source which is coming at the telescope, that is A upon R square. These all terms will again come into the LiDAR equation. Please remember. So this laser power, how much you are photons you are pumping into the atmosphere, how much is transmittance of the atmosphere while going, how much is transmittance of the atmosphere while the signal is received after the interacting with the atmospheric objects, and then you have received. After receiving, you have to acquire the data with the control system, and then you finally analyze the data and interpret it what you want to derive by using this data or these signals. Rather, I will say whatever signal has been received, what analysis, what parameters you want to bring back. So this again I will repeat. You see, transmitter, receiver, transmitter power depend upon NL, lambda L. These all things will come again. Like that, it is transmitted into the atmosphere, the transmitters come into the picture, then these radiations are interacting with the atmosphere, and after the interaction, whatever signal is coming back, this again is propagating through the medium, and the telescope, which basically decide the area of the telescope and range, the solid angle A upon R square, how much signal you are receiving, and this received signal is acquired through control system, and then data processing is done to derive the useful parameters and information from LiDAR systems. Now I'll move ahead further. Sorry. Now I will move ahead further. If you see that what the terms has been shown in the previous slide, that is the LIDAR equation. LIDAR equation is really heart of the mathematics. You can say how the LIDAR uses the mathematics. So that is LIDAR equation. Here all the terms, I will take few minutes to explain you. This is a general LIDAR equation with angular scattering coefficient. Please remember. So this is basically how many photons you are receiving. Okay. This on left hand side, if you see where cursor is there, how many photons you are receiving. And then basically this is LIDAR equation, basically relation between the received photon and how much you transmitted. So if you remove all these things like that, if there is an ideal like that, how much you transmitted and how much you received. So these are the photon transmitted. The second term, this is how much you have transmitted and how much you received. But the receiving does not depend only how much you have transmitted, because it is passing through the atmosphere and the various processes are taking place. So then many terms are there, and all the terms are here pointed very lucidly for you. So the how the LIDAR equation relates the received signal with the transmitted signal with other terms, and these other terms are very important for us because they give us information about the atmosphere. So photon received, how much photons you received, transmitted, that is the property of laser, how much power you are pumping. Then the second term, if you see beta, lambda, lambda L, theta R, delta R, that is basically scattering probability. So you have pumped, but the probability of scattering is beta. Once it is scattered, then how much you are receiving, that is receiving probability, that depend upon the receiver. A upon R square, where A is the area of telescope aperture, you can say primary aperture. And then as you have seen in earlier slide, there are two type of T lambda L R and T lambda R. So one is a while transmitting and while receiving. So T comes twice, you can say as a T square. Okay, so this is transmission through medium. And another term is very important, which is basically depend upon the system, how much your system is efficient. Efficient means different receiving components are optical components, and these optical components are having their efficiency. Or you can say, like you say, photo multiplier tube, which is being used to receive the photons which are coming back. And that all the photo multiplier tubes or PMTs are having the quantum efficiency. So what is the quantum efficiency? And then you are using the optical interference filters and all these things. So they have their efficiency. So this is the LIDAR system efficiency. And then you cannot get rid of the background. So this background may be plus or minus. So the LIDAR equation basically relates relation between the received photon and photon transmitted, scattering probability, receiving probability, transmission through medium, LIDAR efficiency, and background. And this can be further for a given system. For a given system, you can further simplify it. I will not go in that detail. For a given system, for given system and for given place, many things becomes constant, like the transmittance, like fixed telescope area, you can say the aperture of the telescope, laser power. These all the things becomes almost constant except the noise and the scattering probability from the atmosphere. So the LIDAR equation, if I go back again, if you see, these all the terms are there here. All the things with beta, you see the scattering probability, this T transmittance, the while transmitting, while receiving. Then you see this is basically transmitter power, and here it is receiving AR upon R square is received power. Here you see the received power and the data acquisition and processing. So all the terms here, beta, T, transmitted signal, received signal, and area of aperture, how they are related into the atmosphere and in the LIDAR, it is shown diagrammatically here, and mathematically this is the LIDAR equation. And these terms are how they are being used in the atmosphere. You have seen through these slides. Please remember, LIDAR equation is a very important part of the LIDAR. Now I will move ahead and I will give you, I am sorry for little, you can say this blurred diagram, but I will explain you how the really when laser beam passes through the medium, how you can say lidar working, geometrical representation. So here if you see this one, this the bigger cylinder type of thing, this is basically this one is aperture of the telescope. It is the primary mirror of the telescope, and this is the telescope, this one, bigger one. This is field of view of the telescope. You can say this is field of view of the telescope. And for coaxial system, suppose the laser beam is being pumped like this here. The smaller one, if you see smaller, you can say cone type of thing, this is a laser beam. This laser beam, and this is the telescope. So when the laser beam passes into the atmosphere, it is in a field of view of the telescope. Then this is the illuminated volume. This is the illuminated volume, and due to illuminated volume, the signal goes in all the direction. These arrows, if you see, these arrows is a scattering in all the direction, and then the back scattered signal is being received by the telescope. So this is basically geometrical representation. The signal is received only when the laser beam is fully in the field of view of the telescope. So you see this is the telescope, and this is the laser beam, and this is a volume, you can say small volume like that. It is the delta R is the range. I will come again to these things. Here the two sentences I have written. These are very important. Two sentences are there. In the lidar, what you need more and more and more signal, because if the more signal is there, then signal to noise ratio is strong or more, means noise is small and signal is a big. So the higher signal level means high signal to noise ratio. That is our utmost requirement. So from all the altitude regions, what we need, higher signal level, and for higher signal level means higher signal to noise ratio. And once signal to noise ratio is higher, then our precision, or our, you can say, the quality of the data or observation will be very good, and the resolution will be very good. So please remember our requirement: high signal level, high signal to noise ratio, and if both the things are good, then we get the better precision in the lidar, and the resolution is very good. And the second sentence is rather more important. Here, the lidar signal level is a game of what plays important role in the lidar. So lidar signal level depends upon what factors. So these factors are here written in different colors. So lidar signal level is a game of what? Laser power. How much power you are pumping into the atmosphere, number one. Number two, how big telescope you have, telescope aperture, how big telescope you have. And you know, these two things are directly proportional to the money. How much money you have, so you can purchase a powerful laser, you can purchase a bigger telescope. So the laser power and telescope aperture is directly proportional to the funds, how much funds you have. Of course, you need bigger and bigger telescope, and higher power or more power laser, but money, or you can say funds, are extremely important for having the bigger telescope and bigger laser. But you have to have compromise somewhere. Okay, then another thing is effective cross section. That is not in your hand fully, because this is atmospheric process. Effective cross section, as you remember, I told that, please you remember, again I will give you the recap. The effective cross section means that, as I told, Mie scattering cross section, Rayleigh scattering cross section, and Raman scattering cross section. You see, the Mie scattering cross section is order of 10 power 16 minus 16 to 10 power minus 18. Rayleigh scattering cross section is 10 order magnitude smaller than the Mie scattering cross section, that is 10 to power minus 27 or so. Then if you go to the Raman scattering cross section is rather smaller than the Rayleigh scattering cross section, and that is about 10 to power minus 30 or 10 to power minus 32. It is in this range. So that is effective cross section is a very important in signal levels. In signal levels, what is important? How much laser power you are pumping, what is the telescope aperture, and what is effective cross section. And then next thing, which is again not very much in our hand, except in the pollution studies, where you are studying the pollution, the constituent density. Constituent density means how much denser medium is there what you want to study. Like how much aerosol you have, how much pollution you have, how much is the neutral density is there. So beyond certain altitude you cannot investigate the atmosphere by using the Rayleigh LIDAR, because what happens, the atmospheric density is so low, you cannot pump power more than given, you can say, watts into the atmosphere. So you are limited by like that the constituent density. Limited by constituent density means if constituent density is more, then you will get signal to noise ratio better and more signal, higher signal level you will get. And then last but not least, you can say the detector and filter efficiencies. As you have seen in the LIDAR equation, what is important? The LIDAR system efficiency. Here if you see LIDAR system efficiency, so LIDAR system efficiency depend upon all the components, electronics or optical, which are being used in the LIDAR. The detector and filter efficiencies and few more are there which are very nominal. They are not affecting much to our signal levels. So in the LIDAR, you always need higher signal level. If signal level is high, then you have very high or good signal to noise ratio. And once you have good signal to noise ratio, then the precision, or you can say the quality of data, is very good. And for this, for getting high signal level, what is required? Basically, so LIDAR signal level is a game of laser power, telescope aperture, effective cross section, constituent density, detector and filter efficiency, and etc. So this is about how you can get more signal. And previous two slides has shown you how the atmosphere interacts with the transmitted signal, how you are receiving, and how they are mathematically connected with each other. Now, this is a very simple block diagram of a LIDAR. Okay, so it's a Rayleigh LIDAR. Here you see the Nd:YAG laser, which fundamental wavelength is 1064. We generate the second harmonic. We operate with the second harmonic generator, and that doubles the frequency and half the wavelength. So 532 nanometer, and we are using the beam expander. Here, I would like to say little thing like why beam expander is being used. Laser is a unique source of light and it has various properties. And one more property is there. If you increase the beam waist means thickness of the beam of the laser, then divergence decreases. And the basically concept is very simple, or you can say the formulation is very simple. If you increase the beam waist by factor of 2, then the divergence of the laser beam will reduce by factor of 2. So that's what the beam expander is basically very useful. If you expand the beam waist, then the laser penetration increases because the divergence decreases, means it covers the higher altitude. So that was the beam expander is being used. So the Nd:YAG fundamental wavelength is 1064. By putting the second harmonic, you can give 532. If you apply the third harmonic generator, then you can get 355. If you apply the fourth harmonic generator, then you can get 266. So you can, from one wavelength, you can generate basically 3 more wavelengths. By frequency doubling, you can get 532 nanometer. By frequency tripling, you can get the ultraviolet 355 nanometer. Then you can get even the, you can say, stronger ultraviolet signal. If you get the fourth harmonic generator, you can get the 266 nanometer. Here you can use all, you can use 1, you can use 3, you can use 4, and these different wavelengths are being used for using the different part of the atmosphere. That probably I will describe tomorrow in our lecture, LIDAR, Word of LIDAR part 2. The different wavelengths how being used in the different LIDAR systems. So here is a very simple diagram. Laser beam is vertically pumped into the atmosphere. Backscatter signal is received, and the received signal is basically being processed. Interference filter is being used to select the desired signal. Then photomultiplier tube is being used to multiply the photons, because weak signal comes and weak signal is multiplied and then amplify, and then you get the photon counter and all the things, and then you can get in Rayleigh LIDAR the atmospheric neutral density and temperature and so many other atmospheric processes, or you can say phenomena like waves and etc. you can study by using the Rayleigh LIDAR. But basic thing, please remember, the Rayleigh LIDAR does not measure temperature. It measures the density, and from density we derive the temperature, which I will describe in detail tomorrow. Okay, so that If I move further ahead, then this is just a glimpse of our Mount Abu laboratory. Here is a beautiful LIDAR. We have powerful LIDAR. We have laser beam, receiver, and all these things I will describe later in detail about these things. The one more important thing I would like to discuss with you, that is basically many people ask that, or you can say curious, how the LIDAR keeps the vertical information, which signal is coming from which altitude, how the LIDAR keeps the signal, how gives this information. So that is very simple. If this slide is in front of you, please you see the how LIDAR gives vertical distribution to the atmosphere. This is a, I have made it to make it more lucid. It is just like that. If you take, suppose this is atmospheric column, if you take, like you can say bread stack, one bread you take, and then you make the slices of the bread like this one. So the atmosphere is divided into the slices, and these slices are known as range bin, and you can decide how thick slice you want. As you take the brick of the ice cream and you are distributing it, so you can decide how much thick brick, you can say how much thick layer you want to cut. If you want to give someone more ice cream, you will cut the thicker you can say piece, and if you want to give someone, or someone want less ice cream, you will get the thinner one. So here you can decide before operating the LIDAR how you want to probe the atmosphere, or with what range bin or with what vertical resolution you want to investigate the atmosphere. So that's what you can divide it into the slices, and how the slices are being made, that is how the range bin is being decided. This is range bin here, like that. This is range bin. How it is being made? Here I have kept is 96 meter. How you decide it? So the 96 meter correspond to the 640 nanosecond in LIDAR terminology. As I told, R, if you go back, the distance is equal to velocity into time. So R is equal to C into delta T by 2. If you use this formula and you keep the delta T, means time difference 640 nanosecond, then what you will get? 96 meter. So you can say in LIDAR, if you keep the bin width 640 nanosecond, then it will correspond to 96 meter height in the atmosphere. Similarly, if you want the more, you can say the precise slices, then you can reduce this time, and this time and this distance, or you can the range bin, is related with the simple formula. Again I will repeat, R is equal to C into delta T by 2. You can do the simple calculation. You keep C is equal to 3 into 10 power 8 meter per second, and you can keep the delta T 640 nanosecond. I can say in another wording, the 1 nanosecond in LIDAR terminology is equal to 0.15 meter. If you keep resolution, time resolution 1 nanosecond, then you can get the vertical resolution 0.15 meter. If you keep the bin width 10 nanosecond in temporal domain, then you will get the vertical resolution or bin width 15 meter. So you can say that how beautifully you can get the information from the atmosphere. So this was about dividing the atmosphere into different slices. Once the atmosphere is divided into different slices, then laser beam is pumped. When the laser beam is pumped, so if you see here cursor, location of the cursor, when the laser beam is in the range bin number 1, then the receiver is tuned in such a, these are like the buckets. Receiver channels are like buckets, and these buckets are basically numbered according to their range bin. So the range bin number 1 is corresponding to bucket number 1, or you can say the collector number 1. The range bin number 2 is connected with the bucket number 2. Range bin number 3 is connected with the bucket number 3, and so on. This last range bin is connected, or you can say connected with the bucket, last bucket. So when the laser pulse is transmitted into atmosphere, so when first pulse goes into the first range bin, whatever signal comes, it is being kept only in the first bucket. Please remember. When the laser propagates, or you can say pulse goes in the second bin, then whatever signal comes, it is being kept in the second bucket. Similarly, when it reaches in the fourth range bin, then signal is kept in the fourth bucket, and so on and so forth. This process is repeated for several pulses. When one pulse goes, the signal is collected here in different buckets. When the second pulse goes, then again signal is collected. Then third pulse goes because it is pulse laser. Similarly, for suppose the laser is operating at 10 hertz, the laser frequency is 10 hertz, so you are pumping the 10 pulses per second. Okay, in 1 second 10 pulses you are pumping, and you are operating laser, suppose for just simply if I'll say for 5 minutes. In 5 minutes how many pulses you will pump? About 3000. Okay, and these pulses basically going, and the signal per pulse from per range bin is kept in bucket 1, bucket 2, bucket 3, and so on. So like this, the profile or number of photons are collected here in the buckets, and they are corresponding to the different heights. So these receiver channels are corresponding to, or you can say the tagged with the different numbers, and that numbers are corresponding to these different heights, and that's what with from one height, one signal, second height, second signal, like that you are very clearly segregating the signal which is coming from different altitude, because there is no mixing. Whatever signal is coming from the top layer, it will be kept only in the top bucket. So you are very sure this signal, whatever you receive the photons, they receive are from the top bucket. So this, please remember, this is a very beautiful way by which the signal is collected from different altitudes, and you can study the vertical distribution in the atmosphere by using the LIDAR, and you can change the bin width, or you can say range bin width, according to your requirement, what you want to study, or how precise you want to sample the atmosphere, with what resolution you want to sample the atmosphere, you can decide. And you can go to the sub-meter, as I told, you can go up to 0.15 meter, but that doesn't depend upon the pulse width of the laser beam. It is limited by pulse width. You cannot go below the pulse width. Suppose your pulse width of the laser is 10 nanosecond. If it is 10 nanosecond, then it is limited. You can probe the atmosphere at every an altitude of 15 meter. You cannot go below. That is limitation, because the duty cycle comes into the picture. Now, almost I have come to the end of the today's talk, and again I will say like that, this is a beautiful tool and technique, and this is the technique to have the vertical distribution of different atmospheric processes, constituents, and all these by using the pulse lasers which are being used in the LIDAR. So this slide again I will show you tomorrow. Here that tells which LIDAR is known as what. So this is basically physical interaction device and observable. So if elastic scattering is being used for aerosols and cloud, then it is Mie LIDAR. It is being used for aerosol, cloud, and geometry and thickness. Absorption by atoms and molecules, like absorption, so this is dial differential absorption LIDAR, and this is being used for gaseous pollutants, for a study of ozone and water vapor. Then if you exploit the inelastic scattering, then Raman LIDAR is there. By using Raman LIDAR, you can study the humidity, water vapor, aerosol, cloud density, temperature in the lower atmosphere, and atmospheric constituent. Very versatile. Raman LIDAR is very versatile, you can see. Then if you use the only elastic scattering or exploit the elastic scattering of the molecules, that is used in the Rayleigh LIDAR. From Rayleigh LIDAR, what you can study? You can study basically the temperature in the above 20 kilometer, 20 to 90 kilometer. So you can basically stratospheric, mesospheric density and temperature very effectively you can use, and you can investigate the waves by using Rayleigh LIDAR. Then resonance LIDAR. By resonance LIDAR, basically resonance and fluorescence by atoms, that is resonance and fluorescence LIDAR. These are the name of the LIDAR. You can see that physics or physical principle are used for the naming the LIDAR. Mie LIDAR, differential absorption LIDAR, Raman LIDAR, Rayleigh LIDAR, resonance and fluorescence LIDAR. By this you can study the stratospheric, mesospheric density and temperature, wind, density, cloud, up to the 110 or 120 kilometer. That is the beauty of fluorescence. Or sometimes these are type of LIDAR as known as a metal LIDAR also. I will come to that. And then by using the Doppler shift, principle of the Doppler shift, using wind LIDAR, then you can investigate the wind and temperature. Then laser induced fluorescence, if you use, then fluorescence LIDAR. Then this you can use for marine use and for vegetation purpose and all the other investigations like soil moisture and other things. Then if you use the reflection from surface and time of light, then laser range finder like laser altimetry for topography, target, This is being used very effectively for topographic study, for laser altimetry, and etc. So here I will say only that different physical processes are used effectively in different types of lidar to observe the different processes into the atmosphere what are taking place in different altitudes by using Mie LIDAR, differential absorption lidar, Raman LIDAR, Rayleigh LIDAR, resonance lidar, wind lidar, fluorescence lidar, and laser rangefinder or laser altimeter. So this is the world of lidar. I will be with you tomorrow again with this world of lidar with more detail, and you can say more lucid information for you how you can use the lidar for atmospheric investigations in different regimes. And with this I would like to say once again thank you very much for listening me, and once again very sincerely I would like to thank all the people who has listened me. And again I will say there the material which has been used here, the source of the material and diagrams is based on the various research paper by various authors, books, and most importantly the lot of material is available on the web sources. So web resources has been effectively used for this academic lecture. I am sincerely acknowledging all of them and grateful to them for providing very useful academic material which I could use in this tutorial to provide the information about the LIDAR, how the LIDAR is being used, what is LIDAR, and how it is effectively and efficiently used for atmospheric investigation. This is basically end of World of LIDAR Part 1. Tomorrow, I will go further about the LIDAR tools and techniques, how you can use them for investigating the density, temperature, pressure, ozone, constituents, clouds, etc. So, with this, once again, I am thankful to SERF, thankful to the director, Sir Professor Hariom Vas, for giving me opportunity to be with